let's look at density. Density is another concept that's put into the first chapter of a lot of chemistry books as kind of a review of something that you've seen before, but you want to practice using things like scientific notation, and dimensional analysis, and unit conversions, metric prefixes. All of those things can be folded into density problems, and so I think that's usually why they put this as an example of some kind of number of calculations where you can kind of test these concepts out. Rounding off, another one you use. So density is equal to mass per volume. The mass of something divided by its volume. Could be gas, liquid, or solid. Doesn't really matter. So usually we can use the first, first letter of each of these units since they're all different, and D is equal to M over V. Sometimes you see rho, which looks kind of like a P, equal to M over V. So it depends if you're Roman or Greek. You can use D or rho. It's the R. What is it? R-H-O. All right. Well, I'm going to use D because rho looks a lot like a P to me, and that's confusing. And it's good to know that water has a density of 1.00 gram per milliliter at 4 degrees Celsius. And so usually density is written as grams per milliliter. Those are the most common units of density that you'll see. But I guess, in theory, any unit of mass, any unit of volume are acceptable. It's just that it's hard to compare things, right? If you use all random kind of random kind of units for mass and volume, right? You want to use the same units for mass, same units for volume, then you can compare density of things very nicely. And the density of a substance is independent of the quantity, right? Doesn't matter if you have, an ounce of gold or 17 kilos of gold. It's all going to have the same. It's all going to have the same density. And this is, if you're keeping track, this is called the intensive property. It means it's independent, which is another way of saying it's independent of the quantity. Well, just another fancy way of saying that. Okay, so let's look at the density of as you would expect, a gas, such as air. Mixture of gases has a pretty low density in grams per milliliter. Here we have some liquids, right? This is a liquid. Well, I guess we just have one liquid, huh? Water, because wood is certainly not a liquid. Ice is a little bit less dense than water, so it's not a rule that solids have to be more dense than liquids, though typically you would say, gases are less dense than liquids and liquids are less dense than solids, but it's not categorically true. Oh, here we have a couple more liquids. See, this table, I didn't make this table, so there we have some liquids down there. Ethanol and methanol are liquids, and then we have the other ones are going to be solids. So you get an idea of some common densities, and learn something already from that by looking at that. And density is a nice reason, I think, why they also put this early on in the chemistry textbook, is that it corresponds to a really straightforward experiment that can be done in the laboratory, where you measure the density of an object, usually something that you can that's heavier than water, so you can measure water displacement. You take the mass, right, by putting it on a balance, and then you take the volume by starting out with a certain volume of water, and then adding the object and seeing what the displacement of water is, right? That's the change in volume is going to correspond to the volume of the solid object. And so you have mass and volume, and you can calculate density. And so that's a experiment that you might be familiar with. So let's look at the calculations. We're mostly concerned about the calculations here. Given mass and volume, determine density. Okay, well, that's rather straightforward, right? Because we know that density is equal to mass over volume. And so if I have a 5.7 gram block of carbon and a volume of 256 milliliters, we'll say, then density is equal to mass 5.79 gram, and 2.56 milliliters. And really, all we have to do is do the division. I put the numbers in the calculator. I get this number here, but I know something about significant figures, so I don't have to put all those numbers down. I shouldn't put all those numbers down because there's only 3 significant figures, right? 2.26 grams per milliliter. All right, so it's a matter of dividing the mass and the volume, and my answer is in grams per milliliter, which is my expected units here. Well, let's make it a little more difficult, right? I said some of these other things we can fold in here, like let's say instead of milliliters, I've given liters. So now I have to, if I want my answer in grams per milliliter, I have to change the units in the milliliter. So typically, I would do that ahead of time. Say, before I set up the density equation, I would say, what is the volume of seawater in milliliters? So I want my answer in milliliters. So I know that 1 milliliter, milli is 10 to the minus third liters, right? So milli m is the same as 10 to the minus third, right? That's metric prefixes. So that's why I have to know the metric prefixes. And I'm given 1.250 liters. So I can do this conversion with dimensional analysis. I get 1.250 times 10 to the third milliliters. All right? Liters cancel out, and I divide by 10 to the minus third is the same as multiplying times 10 to the third. A little bit of work with exponents there. And now I have the 2 units in the proper proper amount, and that's a really bad D. That's a really bad D there. Okay. Density is equal to the mass, 1.281 times 10 to the third grams, and 1.250. It's getting kind of wavy here. Times 10 to the third milliliters. And I do the division, I get 1.248 grams per milliliter. That's the number I get in the calculator. But I better check significant figures. 1.284 has 4 significant figures. 1.250 has 4 significant figures. So my answer better have 4 significant figures too. 1.2025, right? I have to round up. And that's my density of seawater. What you would expect is it'll be a little more dense than water because it has, inorganic salts dissolved in it. So that makes sense. 1.025 grams per milliliter. So a little unit conversion there, right? Necessary to get the proper units for my final density, right? These are the kind of things that you can throw in there to make it interesting. Okay. Let's see if I got the calculator here. Going to need very shortly. So given the mass and the volume, given density and volume, determine the mass, right? So I know that density is mass per volume, but now I want to calculate the mass. So how am I going to do that? There's a way to do that. Multiply both sides of the equation by volume. Right, and now volume cancels out on the right side, and I can say mass is equal to density times volume. So you don't have to memorize that. You can derive that from D is equal to M over V, M is equal to dV. So what is the mass of a gold brick with a volume of 255 milliliters if the density of gold is 19.3 grams per milliliter? So milliliters, grams per milliliter, looks like the units are going to line up for me, okay. So I can say mass is equal to density, 19.3 grams per milliliter times 255 milliliter, and the milliliters will cancel out because the units agree here, so they'll cancel. I just get a chance to use a red marker, which is really cool. And 19.3 times 255 is equal to, the number I get from my calculator is 4921.5. I think about significant figures now. 3 significant figures in 19.3, 3 significant figures in 255. So my number of significant figures here is going to be 4920 grams. But I want to, probably a good idea to put this in scientific notation. And by moving a decimal place to the left 3 places, I can get 4.92 times 10 to the third, left up, in grams. Right? Or I could change this into kilograms, right? 10 to the third is a kilo, so 4.92, depending on what units they'll accept for the answer. But it's a good idea to switch it into scientific notation or into kilograms, because leaving the 0 at the end of the number there is not. It's a super, it's not a necessary 0. Superfluous is what I was going to say, but that's a big word. But it is a superfluous 0, and better to get rid of that. Well, let's see what else we got here. One more example. Given the density and mass, determine the volume. Okay, so density is mass over volume. Now I want to determine the volume. Well, I can multiply both sides by volume, so I can get volume times density is equal to mass, and then divide both sides by density, and volume is equal to mass over density, right? So you don't really need to memorize all 3 of these equations. You just need to know one of them, and then you can derive the rest of them just by using algebra. So I have a gram of oxygen, or 1.00 grams of oxygen, with a density of 1.43 grams per liter. What's going to be the volume? Okay. Well, grams and grams are okay, so they will cancel out. They agree, right? Put that here. Gram and gram agree, so that's fine. I can leave it the way it is. Don't have to do a conversion there. And volume is equal to mass, which is 1.00 gram, divided by 1.43 grams per liter. And the grams cancel out, and liters, 1 over liters is liters. So I do the math here. 1 divided by 1.43 is equal to 0.699300699. That's what I get in my calculator. Okay, so do I need all those factors? No. Do I need all those numbers? No. 3 significant figures in 1.00, 3 significant figures in 1.43. So here we are, 0.699, and my answer is going to be in liters. I can change that to milliliters, right? A milliliter is 10 to the minus 3. So moving the decimal point over, 699 times 10, moving it to the right, so it goes down. or still in liters here, sorry. I haven't changed it to milliliters yet. Liters, and then 699 times milliliters, right? So I can replace 10 to the minus 3 by milli. So different way I can present this, or do it in scientific notation. 6.99 times 10 to the minus 1 liter in scientific notation. I can also do it that way, but this is working with mass, volume, and density. Here I just put this on here because this might be helpful, is knowing the volume of shapes, because maybe instead of given the volume, you're going to have to calculate the volume. So the volume of a cube is equal to the cube of its sides, right? All the sides are going to be the same if it's a cube. If it's a random rectangle, then you're going to have to multiply A times B times C, right? But the same idea as the cube, right? Just A, B, and C might be different numbers, or they might be the same. For a cylinder, the volume is pi r squared, with radius of the round part, and times the height. And for a sphere, that's not actually a sphere, it's a circle there, but pretending it's a sphere, volume is 4/3 times pi and r cubed. All right, so your meters cubed, or whatever your unit of length is going to be cubed there, right, to get to be volume. So this is something you might want to keep in mind. It might show up in some problems, and density problems, another thing teachers like to do. Well, that's all I have for you right now, and thank you for tuning in.